I want to talk about another way to look at phase changes. Hey guys, we've looked at these a lot of different ways. I mean, if you think about it, and you just answered that second worksheet, I've shown you in terms of an equation. You know, solid plus energy yields liquid. Liquid plus energy yields vapor. I've shown it to you in terms of graphics and animated graphics, where you see the evaporation and condensation in a jar or whatever. You've also seen some scenario questions on it. Now I'm going to put it to you one more way. Okay, I'm going to show you if we graph a couple of different things, pressure and temperature and heat, in a couple of different ways I can graph them, I can actually get some very useful information, and it's going to, actually a couple of things help to explain that we've seen before. Okay, watch. First of all, there's this graph. You have these papers, you don't have to copy these. There's the phase diagram, it's called. The phase diagram looks like this. Now let's talk about this graph. Let's look at it. See if you can figure out, when you see a graph, by the way, we're not really good at interpreting graphs. I've done a couple of labs where I've made you graph things and made you interpret them. And I remember that chapter 4 or 5, periodic table, I gave you all that information in graphic format. Like I was saying how I don't mean graphic, I mean that. Lots of blood. Yeah, right. You had like, there's an increase or decrease across the period, increase or decrease down a group, that kind of stuff. Well, let's take a look at this graph and see if this tells us anything about what we've seen and relate it to stuff that we've already seen, and how it's going to change our definition of some terms here. All right, the definitions that were probably wrong to begin with. Let's start off with the classic question here. What's the boiling point of water? 100 degrees Celsius, right? Or 212 Fahrenheit. No, it's not. And this graph shows that clearly. Actually, this graph isn't the first time you saw that. Remember over here, in this vacuum chamber, what did I do to water in this vacuum chamber? I boiled it at room temperature. It wasn't hot at all. It was actually cold. And this graph illustrates that. This graph also illustrates what happens in a pressure cooker. Let's take a look. All right, here is 100 degrees Celsius. When the temperature is 100 degrees Celsius, when that's the boiling point, all right, that only happens at one place. It happens at 1 atmosphere of pressure, which is about the pressure in this room. If you think about it, how many times I wrote down in labs the pressure, I had you write it down, you had to subtract the water vapor pressure and do calculations, V2, P2, T2, PV equals nRT. It was usually like 762 or 756. It was right around 760, which is 1 atmosphere. The pressure in this room is around 1 atmosphere, and water boils at 100 degrees Celsius or 212 Fahrenheit. But in that vacuum flask, I lowered the pressure down. Now let's see where water boils there. By the way, you can tell the boiling point because this is solid, this is liquid, and this is vapor. Okay? Solid, liquid, vapor. Well, if I lower the boiling point down, the liquid turns to a vapor. All right? Sorry, if I lower the pressure down, I should have done it this way. If I lower the pressure down, the liquid turns to a vapor at a lower temperature. Okay? Which is why I was able to boil the water at room temperature. Okay? And if I were to increase the pressure, like in a pressure cooker, the water boils at a higher temperature. You see? So in effect, what I'm saying is this. Boiling point is not really a point. It's a line. It's this line right here, where it goes from a liquid to a vapor. And it changes. And I'm going to have to redefine, that's why I've got some stuff on that paper. That's why I've got some 3 definitions down there. I have to redefine what we mean by boiling point. Let's look at the melting point. This is a solid, this is liquid, this is vapor again. Here's the melting point. Notice the melting point does not change anywhere near as much as the boiling point does with pressure. That should make sense to us. What do we know about solids and liquids? Are they really susceptible to pressure changes? Do they change much volume or anything with pressure? No. So you wouldn't expect to see a very large difference between the melting point, and there isn't. There's not a whole heck of a lot of difference. And what do you think you call this point right here, Emily, when something goes directly from a solid to a vapor? That's the question she was asking about just a few minutes ago. I've said it several times, and if you look at your notes, you wrote it down under those changes. What is it?
Sublimation.
Sublimation. Okay, I said it several times when we remember I took iodine crystals, purple haze. Remember that? Okay, that was sublimation. I also talked about that same day how dry ice sublimes to give you fog, to give you studio fog. All right, so you've got 3 possibilities here. I could ask you about sublimation, melting, or boiling point. I'm going to define all those. I could also, by the way, this graph will be on the test. I could also ask you to identify solid, liquid, vapor, all right, boiling point, melting point, sublimation, okay? I could ask you to identify all of those points on all of those lines or areas on the graph, and that's what you would tell me they are. You all should be able to, matter of fact, if you haven't already, you should label this as the melting point, this as the boiling point, and this as the sublimation. Now, we're also going to define them down below there. Okay, so label those quickly. Now, we know, I think, by now, why this happens, why the pressure affects the volume, why the pressure affects the boiling point. I've already explained to you. Okay, the higher the pressure, the more I increase the pressure, it's got to overcome that. All right, you're going to see that, hopefully, in these definitions, too. I'm going to come back to this graph in a little bit. But the new definition, yeah, question.
What happens at the triple point? Does it go?
That means all three can exist in, it means all three, solid, liquid, and vapor, can exist at the same time in equilibrium. So in other words, normally, if you have a glass of ice water, and I leave it go, it's going to all become eventually all water or all ice, depending on the temperature. Okay, but at this temperature and pressure, if I put liquid water, vapor, and solid ice together, I could actually have all of them remain in the same amount I have, all right, at that particular temperature and pressure. It doesn't seem possible, but you notice the pressure is extremely low, and the temperature also extremely low. All right, so it really is, that's all it means. Anyway, what was I saying? I was about to say something. Well, let's get the definitions down. I forgot now. But the definitions of each of these. We're going to come back to that graph in a little bit. So you have to realize what the melting point really is, and the boiling point and the sublimation point is a place where the pressures of both of these guys, the solid and the liquid, are the same. Take a look back here for a second. See, this is actually measuring the pressure also, you can think about it as the pressure of the solid and the liquid phase, or the liquid and the vapor phase. Where the two are equal, where the two things are equal, that's what we call the boiling point. All right, and where the two are equal here, the pressure of the ice, the vapor pressure of the ice versus the vapor pressure of the liquid is the same. That's what we call the melting point. Okay, so that's the definition. It's the temperature at which the vapor pressures of both the solid and liquid phases are the same. Normally, to get one guy to the other guy's vapor pressure, you heat him up. But you can also change the pressure to do it too, like I did in the vacuum chamber to make something boil. I'll explain that again in a second too.
So it's just easier to make the temperature change?
Right, exactly. Most of the time, if I want to boil, well, it's not, actually, the point isn't to make water boil 99% of the time. 99% of the time, we don't care if water's boiling. We want water to boil so it will cook our food. We want water to boil so it will cool something down, like the power plant, for example. We want water to boil and turn to steam so we could drive a turbine. We don't want water to boil so we could watch water boil. All right? But I'm just saying, if I wanted to make water boil, I have two options. I can either, the two pressures have to be equal. So I normally increase the pressure, the vapor pressure of the liquid by heating it up. But I could also lower the atmospheric pressure, the pressure above it, all right, and let it to make it boil that way. All right, so that's what boiling point is. The temperature at which the vapor pressures of the liquid equals atmospheric pressure, or the vapor pressure above it. So as you copy that down, let me just, do not draw these. I'm just going to show you one more time. Don't have to copy this, just watch. All right, just watch. Here's a jar of water, okay? Sitting there by itself, if I let a jar of water or a beaker of water sit there on the counter, over time, it's evaporating more than it's condensing. There's some pressure above it, okay? But it's certainly evaporating more than it's condensing, so a couple of weeks later, I got no water left in my jar. I want to make it boil. I want to make it evaporate spontaneously. I want to make it, basically boil. So I'll put it on a flame. Here's my burner, okay? Candle, whatever. And so right now, okay, the pressure, the vapor pressure of the liquid, all right, is not quite equal to atmospheric pressure. Okay, but I'm going to make it evaporate faster and faster and faster, such that I will increase the vapor pressure of the liquid, so it becomes the same as the pressure above it. That's normally how you boil something. But when I put something in a vacuum flask, I'm not going to make it evaporate any faster. I'm just going to suck this stuff out. And we know that has the same effect according to Le Chatelier's principle. Liquid plus energy yields vapor. If I remove vapor, right, I'm going to favor which direction? The forward is going to try to replace it. So much so that it will try to replace it. The pressure above it is lowered so much that eventually it's going to be equal to the pressure of the liquid trying to evaporate, and it will spontaneously evaporate. Okay? Lastly, of course, you have sublimation, which is the word you were looking for in that last thing, and it is written above the arrow for solid going to a vapor. Sublimation is changing directly from a solid to a vapor. Seen it before, both in a demonstration and in the equation, and now in the definition. And basically, that occurs when solids have a vapor pressure close to atmospheric pressure. I know there are certain things that do it more easily than others, like, for example, iodine and dry ice. But even water does. And I use it as an example. I open my freezer on a hot summer day, and I see steam come out. I don't see liquid water dripping out of there. I see steam come out. And that's because solid ice is going to go directly, it's going to sublime at least a little bit. Even that snow out there. I mean, we haven't had a whole lot of days. There hasn't been any rain. There hasn't been a whole lot of days above freezing, but it's getting less and less and less snow because it, too, is even evaporating. Subliming, I should say. Going directly to a vapor. You haven't seen a lot of puddles around, but there is less snow out there. We'll be shoveling the courts today. I wish there were less snow. All right. So that's just another way of looking at a graph of pressure. Let's go back. Of pressure versus temperature. Okay? Pressure on this side, the y-axis, temperature on that side. I would ask you on a test to possibly identify any of those sections, including the axes. Now, let's look at a different graph. Check this one out. That's also on your paper. Okay? Now this graph doesn't seem to make sense. Let me tell you why. Let me get rid of just the graph part. Here's what it should look like. The graph, for all intents and purposes, should look like this. If I'm going to heat something up, if I've got heat down here and temperature up here, if I simply put water on a stove and put a thermometer in it, and I measure the amount of heat, the longer it's on the stove, the more heat it's getting, I should get a graph that looks just like that. The longer it's in the hot water, the longer I'm on the stove, the hotter the water should get. But I don't get that. I get something completely different. I get this. What is going on? Let's take a look. Instead of just going straight up, this stuff goes up for a little bit, and then it stops going up. Then it goes up again, the temperature, as I'm still adding the same amount of heat. But then it stops going up, and I'm still adding heat. Why isn't it increasing in temperature? And then finally, it goes up again. But the whole time, I'm adding a constant amount of temperature. What's going on here? That's what I want to talk about. All right? Well, what's going on is, at the, what do we call this phase right here? This is the, we'll use different colors. Solid, right? This is a solid phase. From here to here is a solid. If I were to put numbers on this and it were water, look, watch. This would be 0, and that would be what? 100. Okay, so there's the solid phase. What's happening here? What's it doing between here and this is going to be the liquid phase there? This is the liquid phase. That's melting, right? So the liquid phase is right there. And then, of course, I've got the vapor phase up here. Between the liquid and the vapor phase, what do we call that? Evaporating or boiling, right? Right? Okay. At each of the phase changes, you have no temperature change. It's not rising because all of the energy that you're adding, and you are adding more energy, all the energy you're adding is going into changing the phase. In the case of a solid to a liquid, breaking down that crystalline structure. That crystal was all nice and neat and ordered. It takes energy to break that apart. And vice versa. Watch this. I took these crystals. I did this once before. You may remember. But only those people here. There's a lot of people absent that day. I took these crystals, okay, and I melted them. Put them in a beaker of water and melted them, like this beaker of water right here. Okay? This beaker of water right here. Showing people at home. Who's not here today?
Maddie.
Maddie. Trent. This is the beaker of water. All right. Then I filled this beaker. I poured out the hot water and I put cold water in. And that cold water right now, that's what it is. It feels very cold. It's just cold water. I'm holding it in my hands. It's obviously not hot anymore. But I've cooled this stuff down. Why didn't it turn back into a crystal? Well, it didn't have anything to freeze around. I'm going to add one of these crystals. Remember, what's that called when I add this crystal to this guy? Seeding or nucleation. Good. All right, let me add some of this. Let me add one of these crystals to this guy and see what happens. This, by the way, is sodium thiosulfate. Now, that's a liquid. You can see it's a liquid. It's a cold liquid. I drop this in here, and for those of you at home can see it better, those of you who are here can see it too. Watch what happens. Can you see what's happening there? You people sitting here? Can you see it? It's freezing. It's freezing. It's turning from a liquid to a solid. Hopefully you can all see that. Turn the light on, you can probably see it better. Should have done that earlier. Okay, it's freezing. It's now frozen solid. So is it cold? You guys who are here now, I'm going to pass this around. It's unbelievable. Surprisingly, it's hot. Hold it at the top because it's really, really hot. And just touch the bottom as I pass it around. What the heck is going on? Turn that light off again. Front light. What the heck is going on? Well, I'll tell you what's going on. Look here. Here's your equation. Solid plus energy yields liquid. Okay? Look up here. This is what's going on right there. Okay? That's what's going on right there. This explains both parts. Everybody watch this. Hold that for now. Don't pass it around. Just hold it and watch. Everybody watch this. This explains both things. It explains why there's no change going that way. Because basically, I have to break up all these crystals. It takes energy to break it up. But we know the law of conservation of matter and energy says what? You put energy into something, it's still there. You can't create or destroy it. So when this stuff goes back this way, when I'm going from a liquid to a solid, what you just saw happen there, when it freezes, what does it give off? Energy. Now, all you are probably saying, well, why doesn't ice feel hot then? The answer is it does. When ice freezes, it releases energy. It's an exothermic reaction. It doesn't feel hot to you for a very simple reason. Your body temperature is above the temperature at which it's releasing heat. But it's giving off heat, just like that guy's giving off heat. I can feel him because he's giving off that heat at the temperature above your body, or I'm sorry, below your body temperature. I can feel it. He's giving it off there right now. You can feel that heat giving off. Don't put your finger inside of it, Emily. All right. Okay. You can keep passing that around now. But with ice, it's happening in a body below your body temperature. Here, it's above your body temperature, so you can feel it. Okay. All right.
The longer you hold it, the hotter it gets.
If you say so. Now, let's take a look. By the way, it also helps to explain this. It helps to explain my grandmother's misunderstanding of chemistry. My grandmother used to say to me, I remember when I make tea, if you want tea, she said, leave the water on for another 5 minutes. I want it to get hotter. Is that going to happen? Is tea going to get any hotter by leaving it on for the water boiling for another 5, 10, 15 minutes? No. It doesn't get any hotter because the temperature is all the heat's going into changing the state from liquid to a vapor. Let's go back to our popcorn example. Remember I told you popcorn burns you worse. When you open that bag of microwave popcorn, it burns you worse. Remember that? Okay. I told you there's a reason for that. Liquid plus energy yields vapor. I could ask this question on the test as one of those scenario questions. Did I ask it yet on either of the worksheets? I don't think I did. I can. Why does popcorn steam burn you so badly? The answer is at least twofold. One is, as the vapor hits your cold hands, it turns into a liquid. It condenses on it. What does it give off when it does that? Extra energy. Now, a lot of you are saying, well, it also burns you just because the steam is hot. And you're absolutely right, steam is hot. But if you put the steam is not as hot as you think. Okay? What temperature does steam water boil at? 212. So 212 isn't that hot. But now we have a second way it burns you. In a closed container, in that popcorn bag, sitting in a microwave oven, it's closed. You can actually boil all the water off and turn it all into steam. So the temperature of that steam actually gets up above 212 or 100 degrees Celsius. So you're being burned because the steam is hotter than, if I put my hand over steam on a boiling pot of spaghetti water, is it going to burn? Not really, right? I can hold my hand over that. But I can't hold my hand, if I hold my hand right over that popcorn steam when it opens up, I'm going to get really badly burned, all right? For a couple of reasons. That steam is hotter. It's giving off the energy as it condenses. All right, and by the way, there's also a lot more of it there, condensed in a small space versus spread out over an open stove where you just put your hand over a boiling pot of spaghetti. All right, so hopefully you understand now why this graph looks like this, because I tell you right now, that's what we're doing tomorrow for calculations. We're going to learn how to calculate how much energy it takes to melt or raise the temperature or boil or whatever. There's actually 5 calculations in here. There, okay? Just raising the temperature of a solid, a liquid, or a vapor, and melting or boiling liquid or a solid, okay? All right, now, write these last little notes down underneath here. So, just in summary, what I just said a little bit. No change in temperature, as you can see, occurs as the phase changes. Why? Because you see that? Right there, right underneath. All of this energy is going into changing the phase. It's not breaking down the crystal or moving the molecules of a liquid further and further apart. So all that energy is going into changing the state of the substance. Now, like I wanted here, about 20 minutes for you guys to have some time to get that quiz done. So as soon as you're done copying that, the 6 people have to make it.